Hi, everyone. This is an update on some work that I've been doing to model the scattering properties of icy regolith at radar wavelengths. My co-authors are Wes Patterson, Lauren Joswiak, Josh Cahill, and Angela Stickle. All of us are at APL. And this work was supported by the wonderful LRO Mini-RF radar team. The motivating question behind this work is really a basic one. What does icy regolith look like at radar wavelengths? Radar is a particularly powerful technique when it comes to the search for water ice in PSRs because of the ability of radar instruments to both see into shadow and into the subsurface to tens of centimeters or tens of meters, depending on the wavelength. But we've known for several decades that not all ice-containing regoliths look the same to radar. Mercury, the other body in the inner solar system with icy poles, has very clearly defined, very radar bright polar deposits. You can see them pop in the Arecibo image here. And from the superimposed values, you can see that those radar bright polar deposits are also characterized by very high values of CPR. And CPR in this context is the circular polarization ratio, not Colorado Public Radio, as I learned yesterday. And you can think of that as a measure of how strongly the polarization sense of the incident wave is preserved in the return signal. That's the first time I've explained CPR without taking a whole 10 minutes. On the moon, the situation is a little different. Some polar craters, and in particular, some polar craters that we know to contain water ice, like Cabeus, have been found to have an unusually low CPR. Often they have CPRs that are lower than the surrounding terrain. And so that raises the question of how do we identify ice in radar observations of the lunar poles? There are several ways to answer that question. We take a modeling approach. We can frame the question in physics terms as one of how radar waves interact with a scattering subsurface volume. And we take a Monte Carlo approach to solving that problem. We begin with an incident electric field vector. As the radar wave moves through the medium, the incident electric field vector changes due to scattering and attenuation within the medium. And then the exit electric field vector that comes out is different. There are many possible paths through a subsurface volume, and if you model a large number of those potential paths, you get a large number of exit electric fields. You put all of those together and you can start building up a picture of how polarization properties change as a function of, for instance, incidence angle, and also as a function of phase angle, or in radar speak, bistatic angle, which is that angle between the transmitted and received radar signal. To perform this calculation, you need to make a few assumptions about the nature of the subsurface, and that's where things like the composition and the size and shape of scatterers come into the picture. These are some representative results. So the plot up there shows CPR as a function of phase angle for 4 different kinds of subsurfaces. In all 4 of the cases, the scatterers are assumed to be spheres, as they always are in real life, with a certain size and size distribution. The only thing that varies is the composition of both the scatterers and the medium that they're embedded in. And we update those values and change them, play around with them based on the dielectric properties of rock, regolith, and ice that we draw from the literature. And so first of all, you can see that our icy mixtures, so our modeled ice with either scattering void space or scattering embedded rocks, those are shown in blue, dark blue, tend to have a stronger, narrower opposition response, that uptick in CPR towards zero phase, compared to regolith with embedded rocks, which is shown in light gray. At the same time, our modeled icy substrates still have a relatively low CPR compared to what we see, for instance, at Mercury. And in this case, we think that that's very likely due to the relatively low volume of scatterers that we include in these particular model cases. We can be ambitious and overlay some real live mini-RF bistatic observations shown there in the neon colors. And you can see that there are some resemblances between the observations and the model results. So for instance, the presumably icy floor of Cabeus crater has this narrower, steeper opposition response compared to the more rounded response that you see in the Kepler ejecta, which is non-ice bearing. But at the same time, we're not yet at the stage where we can conclusively relate observations to model parameters. You might also have noticed that there is one of our model cases in which the CPR is unusually low, as we might see at some polar craters. And that is the case where we have icy scatterers embedded in regolith. And quantitatively, the amount of ice we're modeling is on the high end of what's derived from the L-cross measurements. And so since this is a model, we can dig into and investigate the physical reasons for that low CPR. And in this case, what seems to be going on is that ice and regolith are likely to have very similar dielectric properties. That's something that's been noted before by others. And because of that low dielectric contrast, radar waves traveling through that icy regolith mixture travel on long scattering mean free paths through a relatively absorbing medium. Regolith absorbs radar more than ice does. And that combination of factors seems to be what leads to the low CPR and the weak opposition response near zero phase that we see in that case. There are a number of other things we can look at. Those were some representative results. I've talked mostly about CPR so far, but there's recent important work that suggests that CPR by itself is not a reliable indicator of the presence of ice, even at mercury. And so we're also interested in the process of investigating other polarization properties, such as, for instance, the intensity of the return signal in the same circular and opposite circular polarization senses. As you can see in these plots on the left or right, some side of your screen, gets very confusing, but I'm doing okay on time. We're also interested in incidence angle effects. We've looked at this a little bit. It gets complicated, and we're in the process of trying to figure out what the incidence angle effects that we see in the model mean when it comes to interpreting mini-RF observations. This is also a good time for radar at the moon. Both the LRO and Chandrayaan-2 spacecrafts are currently acquiring radar data at several different wavelengths. Those see to different depths into the subsurface, and they also respond differently to dielectric properties, which are sensitive to wavelength, and we'd like to be able to model all of those scenarios. There are also several other configurations that are particularly interesting and that you can look at with a model like this. So for instance, what would you get if you had ice layered beneath a relatively dry overburden of regolith? What happens if you have other materials that I haven't talked about? What happens if you have a fine-grained ice regolith mixture or a porous ice matrix? So those are some of the things that we're in the process of investigating. So stay tuned, and we hope to have more results to share with you. Thank you very much.
Thank you, Parvathy. Any questions in the room or online? How are we doing on time? Okay. Norbert?
No questions online.
Okay, I've got a question that probably shows how much I don't know about radar, but is it worth comparing with what's known about at least icy moons from radar to get a sense of what's happening, or are those measurements non-comparable?
Yeah, that's a really good question, Amanda. So the really icy, the unambiguously icy moons of the solar system have CPRs very comparable or even higher than what we see at Mercury. So we're sort of using Mercury as kind of a limiting case of relatively pure water ice deposits.
Right. Okay. Got it. Thank you.
But if we model, for instance, a porous ice case, it would be interesting to compare that to what's the CPR value of Europa or something.
Right. Okay. Great. Neat. Well, this is really great. Thank you. Thanks. Okay.
I have a question, Parvathy. Go back to your modeling results.
These?
Yeah.
Yeah.
Sounds like the ice-bearing materials has very low, much lower CPR than the dry regolith, right?
Yes.
Why don't we search some low CPR regions, very low CPR regions?
Wait, say that again?
Because the ice-bearing regolith shows very low CPR, much lower CPR than dry regolith. So that means like if you find something showing very low CPR on the lunar surface, it could be ice-bearing.
Potentially. So, we'd want to sort of explore the parameter space more before, saying that conclusively, but yes, one potential reason for anomalously low CPR regions could be that, perhaps, and so as there's a paper by Wenju Fa, and so I think the way he puts it is that, low CPR might not be due to the presence of ice as much as it is due to the absence of rocky scatterers. So yeah.